Morning. So we are continuing with 4.5.4 trigonometric functions on unit circle. The difference between this section and the previous one is we took trigonometric functions on any circle. R was defined as a number other than 1. And in this section we took it 1 and our sine t turned into a simple y instead of y over r. It used to be y over r. Since r is 1, it's y. Cosine is x, cosecant is 1 over y, secant 1 over x, etc, etc. Okay, so yesterday we learned about the unit circle wheel. This wheel helps us figure out any angle, any trig function, any angle from 0 to 360 degree. You may say, oh, there is no tangent here, only sine and cosine. You're right, this is cosine value, this is sine, but when you take the ratio sine over cosine, you get the tangent. So it takes a moment to get everything, okay? And we learned about periodicity, which is if you have an angle more than 360 or a negative angle, you'll feel free to add multiples of 360 until it's a measurable number from 0 to 360. So such as we had a value 690. Oh, this is pretty big. So you can reduce it 360, 360, 360 until this thing falls into an angle that's measurable by the wheel. You don't need this many. I think we did it twice and we got here 330, and 330 cotangent can be found from these values. You just take y over x, or no, x over y, sine, cosine over sine, which was negative root 3. Okay, so periodicity helps us figure out big negative, positive, big values to drop to the perfect size 0 to 2 pi again. Now what is new today is we learn about evenness and oddness of cosine and sine to help us figure out negative angles. Look, finding negative angles is always a pain. Like cosine, I know cosine 30, but I don't know cosine negative 30 on top of my head. I wish this was cosine positive 30, then I could just take a look at the table. I know the table of cosine from 30, 45, and 60. I could just answer that. Well, there is a solution for that. Cosine is called an even function. That means cosine positive angle and negative angle doesn't matter, they are the same. So evenness means when you have a negative of the original value, a good value, you can just ignore it. In other words, delete that negative without any cost. You can delete, wipe off the negative and consider it as cosine 30. Well, what other functions are even? It's cosine, secant. How come secant is also even? Because secant is actually 1 over cosine. It's 1 over x, 1 over cosine. So if cosine is even, of course 1 over of it is also even. Okay? Well, what else is even? That's it. 2 of them only. Cosine and secant. So from now, when I ask you a secant of a negative 300, for example, degrees, oh, I can wipe off the negative and compute instead 300. They will match. Okay? Make sense? About oddness. What does oddness means? On oddness, unfortunately, you are not allowed to wipe off that negative sign. No. The remaining 4 are odd. Sine, cosecant, tangent, cotangent are all odd. That means if you have a negative 30, for example, you can't wipe off this negative. However, good news, you still can do something about it. You can bring that negative out and compute the positive angle, that is 1 over 2, and bring this minus in, negative 1 over 2. Again, you can't wipe off, no wiping off, no wipe off, but moving out. You can move it out. Again, why we need to do this? Because we hate computing negative angles. We already built all our charts. Look, all of this wheel, all the previous charts are for this one positive angles. So you memorize them for positive. You need to think about negatives for a minute or so. So why don't we shorten our waiting period and just get that minus out of our way? Either you wipe it off if you're lucky to have cosine or secant, or bring it out front if it's one of the other 4 trig functions. Okay? Alright, let's do this question now. What you need to do is use periodicity to 2 concepts, even and oddness, and this is from yesterday. This is from even and oddness. You're going to use these properties here in this left side and bring this into one trig function. You're going to get rid of stuff, reduce this. Alright, what can I do here? First off, I see a negative sign which we don't like, right? What can I do about this negative sign? Can I just wipe it off? Alright, I'll give you a minute to think about this. They actually give you a clue. These will turn into cotangent t with a number in front. You just need to figure this out. What number many times cotangent t is the answer? Think about it. Again, this is what we have. Evenness, oddness properties here. And from yesterday, we know that sine, cosine, secant, cosecant have 2 pi period. So when you add 2 pi to their angles, they are still the same, or subtract. Tangent, however, and cotangent as well, have only pi period. This, that, make use of them to simplify this guy into one cotangent. What number did you get? Come on, anyone? Alright, we have one candidate answer. -2 comes here. What other numbers results did you get? Did you get the same thing? Alright, let's do this together then. First off, evenness property, oddness property of cotangent says if you have a negative sign inside the angle, right next to answer inside the cotangent, we can move it out. Cotangent is odd, so we can bring this minus out front and combine that with this guy, and they become a positive cotangent t. Okay? Alright, how about this one? How do I get rid of this and make only t? Because in the result I need to have only t. I need to get rid of pi. What do I know about cotangent? And what happens if I add pi to its angles? They are the same, yes. cotangent t plus pi and cotangent just t, no pi, the same. How do I know that? From the periodicity table. It says if you add multiples of pi to cotangent, it's still cotangent t. Okay? So we have minus 2 of them. Alright, you have a secret one here. You have plus 1 cotangent, minus 2 cotangent. In total, how many cotangents do you have? Negative 1. No, minus 2 plus 1. It's the minus 1. The answer is minus 1 then. Alright, what is this about? Oh, this is the wrong class. Makes sense. Alright, well, I'll come back to this and substitute later. Alright, why don't you guys think about the second one? Same deal. Use periodicity of sine, and this time sine is also odd, so this is kind of similar. Oddness of sine and periodicity of sine, use it to combine these two. You're gonna combine them to single sine. Again, use this one. Any results? Come on, it shouldn't take that long. Negative 15. Is that right? Is that the same answer you all got? Alright, let's check out. When I add sine of an angle 2 pi, it's still the same, because sine is 2 pi periodic. So this is just sine of 90 minus 7 many sine 90. Alright, sine is odd. Odd means when you have a negative number inside, you can move it out. So when I move this out, only the minus sign, not 9. Don't bring 9 out. You cannot do that. Plus and minus combines into minus 8 sine 90. Well, you have minus 7 of them, and minus 8 together. In total, you have minus 15 sine 90. Okay? This looks negative 1. Alright, until it loads up, why don't we take a look at next question. Again, there is nothing new in this section today. We're just using our past knowledge and what we just learned to make different kind of questions, okay? Alright, what is the question here? You are going to write tangent in terms of secant. Turn tangent into secant using one of the identities here. I don't know which one, you need to pick one. However, there are two parts. In part A, you are going to consider this angle in quadrant 1. In part B, you are going to consider it in quadrant 3. Why? Why should I care about that, what quadrant that T is in? I don't know. First tell me, which identity helps us convert tangent into secant, please? Which one? Which equation here has tangent and secant involved? Yeah, it's Pythagorean identity. Tangent square plus 1 is secant square. So I start with that. I flip theta to t because in our question is t. Now I need to get tangent alone. This is with a square. It says only tangent. Change tangent. This is a square. So I need to leave that alone by subtracting from 1 from both sides. Alright, what else? How can I get rid of this square now? Square root. And tangent t is secant square minus 1 under the square root. That's it. That's what I'm gonna type in. Am I right? Or I'm missing something. I haven't used this fact. I'm afraid there is something fishy going on here. We haven't used it. We should have used it somewhere. Am I forgetting something? Okay. You're Madison. Courtney. Courtney says this data says in quadrant 1 all 6 trig functions are actually positive. Tangent is one of them. This says tangent is positive. I need to use positiveness of tangent in this process, but I haven't used it. That's a good point. This means this is to imply we need to go with the positive option. I don't have an option here. What am I missing? I still don't see any use in this process. Positiveness. Where should I use? What am I missing? Nothing?
When you take the square root of something, it's also positive and negative.
Right. You take square root of both sides in an equation with unknowns. You need to put plus and minus. There are two options here. You can't put both into the answer box. You need to pick one. And we go with not this one, but this one. Yes. Because square root, a negative in front, is gonna be a negative number when you put angles in. And we know tangent is positive. So we go with the positive option. Okay? That's what I'm going to type in here. Just the positive secant square t minus 1. Okay? Alright, guess what's going to happen in quadrant 4? Well, I need to figure out the sine table for tangent on quadrant 4. This is quadrant 4. No, 3. It says 3, right? Sorry. Quadrant 3. What is the sine of tangent? No, you don't have to cheat, okay? Just look, pick a point and see what tangent is. First of all, any point here What kind of x and y values? What kind?
Negative.
Negative, negative. And tangent of this angle is y over x, right? It's negative over negative. What is negative over negative? So again, we are going to go with the same answer, positive answer. So copy this and put it there.
That one's for quadrant 4.
Oh, this one says quadrant 4. Oh yeah, thanks. Yeah, it looks like my question flipped. Here it says 3. So in quadrant 4, what is it in quadrant 4? This thing is negative. The second one is still negative, but the x is positive this time. If x, this is negative, but if this is positive, negative over positive is negative. So this time we're gonna flip. Okay. Alright. Let's see what's next. No, nothing else. Oh yeah, 8 and 9, I just put 2 random questions, kind of review type questions. You're just supposed to compute sine of 4 pi over 3 because you have so many tools now. You can use reference angle, you can use the wheel, okay? Get these trig functions. And number 9 is also a simple question, I think. You're gonna figure out what angles makes tangent undefined. And we already figured that out yesterday. Tangent becomes undefined at odd multiples of pi over 2, right? So it's 1 pi over 2, 3 pi over 2, 5 pi over 2. These are bad values for tangent. So anytime your angle stops on the top or bottom, top, bottom, top, bottom, top, bottom, and when it's rotating, tangent gives us a problem. So you can figure that out. Alright, this is it for 5.3, 5.4. Any questions? We are starting 5.5. That will be our final section before the exam 2. Okay? 5.5 is about graphs of sine and cosine only. And the 5.6, the next section, will deal with graphs of the other trig functions, tangent, cosecant, secant, and cotangent. The most important ones are sine and cosine. You definitely need to know what they look like and how to manipulate them, change them. Alright, well, what is the common method you've been using graphing any kind of function since elementary school? Table method. You pick an x value, you compute y value from the equation, pair them up, put that dot on the picture, connect the dots, there you go. You have the picture. And somebody, thank God, did it for us because it's really time-consuming procedure. You need to evaluate sine at 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3. Somebody did it for us. Actually, they've just copied it from this wheel. Oh, look, all these values are here. Sine 0, no, sine 0 is here. Sine pi over 6 is here. Sine pi over 4, pi over 3, pi over 2. They're all on the wheel actually. They just carry it to the table. Well, it's still something. Now what you need to do is you pair this up. This is, for example, 0, 0. Oh, it's this point. There you go. Put a dot there. Pi over 6, 1 over 2 is the next one. By the way, how did... no, they didn't put it here though. But it's right there. This point. They didn't mark it x coordinate, but we know where it is. It's this one. And then they did pi over 4 and root 2 over 2. By the way, how did they know pi over 4 is here? How large is pi over 4? This is how they compute pi over 4. Pi is 314 something. You divide it into 4 pieces. So you get about 0.7 0.76 something. So this is about 0.76. This is about 1.5. This is about 3.14. That's how they measured. This is about 6.28, 2 pi. Okay? You just take a ruler and go 6 units, okay? When they connected all these dots, they first rise up to 90 degrees or pi over 2, because sine gets bigger and bigger. Like this value is almost 0.8, and it maxes out. Maximum is 1, and it never goes beyond 1. Look, the maximum is 1, and then it starts dropping again. This is 0.8. This is about 0.7, I think, something. And this is 0.5. Look, the values are dropping. It's 875. Again, you're dropping, sliding. So rise, slide. Further slide to negative, and then it starts becoming negative. Look, negative 0.5, negative 0.7, negative 0.8, and negative 1. You slide all the way down and make a deep down point value, -1. And then you hit the bottom and then climb up again. Climb up, slide down. Climb up, slide down. Up and down. It's a roller coaster. Sine is going up and down. This is called an oscillating movement. Goes up and down. It kind of repeats the same act over and over. Look, let's put a frame like a photo picture. Somebody cut this out, this part. I'm cutting this out. Cut it really out. Double it, copy it in a copier machine, and they put it next to this guy. Oh, I don't want that. Where's my box? Alright, they copied this and put it here. Copy it to the left, copy it to the right, and you keep copying that same move, up, down, and a little bit up. This move keeps repeating over and over. This frame I circled is called one period movement, because this is repeated over and over. This is called a period movement of sine. You need to know this frame by heart. Know this, because when you copy it, you get the whole picture. This is the one we are going to use when we are graphing more sophisticated variations of sine graph. You always will start with this frame, and you will shift it up, down, and stretch or shrink it, or take symmetry of it. You're going to flip the cross x-axis. Well, you are going to just play with this piece on it. This is your Play-Doh. Okay? So copy this into your mind. This is what sine is. It starts at 0, goes up to 1, goes down to -1, and comes back to 0. Got it? Memorize it? Well, you know how to get it if you forget. You need to create this table on your own if you forget it. And then plot these dots. Alright, this is sine. Coming up next, guess what? Cosine is next. Alright, again from the wheel, somebody created all the angles from 0 to 360 and cosine values. What is the first difference what you see? Sine was starting at 0, 0 right this moment. Where is cosine starting? Up here. So you're not starting on ground level. Your roller coaster is up in the maximum, and you slide, take a big slide, and go hit the bottom and come back up. This is the one period movement of cosine. And take this frame and never forget. 0 to 2 pi gap piece is what you need to write to your mind, okay? Again, it's similar to sine, right? almost identical, except this guy starts at 0. At pi over 2 it becomes 0, and at pi it hits the negative value. And somebody just copies this from end to end. Cut, copy, paste. Cut, copy, paste to the left. Keep copying it and connecting it to the previous piece. You get the entire oscillating movement, up and down, roller coaster, indefinitely. It goes all the way to the right and left. Make sense? Now here is sine and cosine together for you to see the difference. Do you see the difference? Kinda cosine has a lag. This is a lag bit of pi over 2. It follows sine pi over 2 behind. It's behind pi over 2. Like you're already on this train moving up and down. The guys are just tracking you behind pi over 2. Time lag. Yeah, okay? But they are making the same level of maximum. They never pass 1 or minus 1. They make exact 2 pi repeating movement, 2 pi period. There's just a small lag between them. Make sense? So this is it. Let's go. We're done. Now, this is only basic graphs of sine t and cosine t. In life, in your problems, you won't have just sine t, but sine 3t, or a number before, or a number after, or a number dividing. So how do you change these pictures if your function equation changes slightly, not major change? They will be adding numbers before and after sine maybe, okay? Alright, so we are going to sketch things like this. There is a number in front of 4. How is this picture gonna change? Okay, there is a number inside cosine and before. How do these change cosine graph? Now there is a number everywhere pretty much. Look, before x, inside, after, not before sine though. Okay, how do you make your new graphs from old ones? This is our concern. But before that, why don't we observe, we already observed this, why don't we list some of the common properties of sine and cosine we experience from these pictures. First off, the domain of both functions is everything. Every number you insert into x, you can compute its sine and cosine. No exceptions. Sine and cosine never becomes undefined. It's clear from the graph. There is no holes, no interruptions, no jumps. Sine and cosine have negative infinity to infinity domain. Their range is between -1 and +1. They never leave out this zone. They live in this neighborhood always. Between -1 and 1, they go up and down like a wave. And they both have period of 2 pi. They keep repeating the move every 2 pi. Next, sine is symmetric with respect to origin. Look, you have this piece repeated here, symmetrical with respect to origin. However, cosine is not. Cosine is symmetric with respect to y-axis. Look, left piece and the piece on the right. Okay, symmetric with respect to y. These guys symmetric with respect to origin. Look, left, right, left, right. Cosine is symmetric with respect to y. Sine is symmetric with respect to x. Because sine is an odd function, cosine is an even function. What does odd mean? If you have a minus inside, you can pull it in front. That's oddness. If you have a minus sign, you can pull in front, it's oddness. Cosine is even. Symmetric with respect to y means even. That means if you have a negative sign inside cosine, you can just wipe it off. Make it positive. Again, there is a lag of pi over 2. There is a shift. Once you shift one of them pi over 2, the other one catch up with the other one. They overlap. Only they differ by a horizontal shift of pi over 2. Move one of them pi over 2 right or left, they match each other. Okay, now we're starting our first transformation. What happens to graph of sine or cosine if you put a number in front? Actually, this is not new. We have seen that in 2.7. Do you remember that section? Transformations of graphs. What happened to x squared when you put 2 in front? Parabola x squared, when you put 2 in front, it stretched up, right? It moved, kind of branches went up. Same deal here. It depends on the size of the number. If the number in front is more than 1, if it's more than 1, it's going to stretch up. If it is less than 1 but more than 0, it just shrinks down. It just, this bump, do you see this bump? It gets smaller, like this. If a is less than 1, this bump gets really high up if a is greater than 1, depending on the size of a. What if it's negative though? These are true if a is positive, like 1/2 and 5. What if you have a negative 2? Then that negative sign is going to reflect the picture down. Negative number will move it down if a is negative. A negative, you flip it down, and this piece will flip up. Make sense? Okay, you will get it once we do this. So what do you think 4 will do? There is a bump and cavity here. It's like a cavity here. This is a bump. This is the ground level, right? It's going to make this, every shape here, there is a mountain and valley. It's gonna make mountain higher, valley deeper, right? How much? With a scale of 4 times. So, alright, here is the catch. Any point on x-axis, let me mark them. These are x-axis values. These are nailed. They do not move. Don't move this. Some people think, oh, this is 4 times up, so I'm going to move these up like this. They move it and make it really big hill and big cavity. No, we don't move those red points. Red points are nailed, like you nail them. Only this elastic part, let's say it's rubber, you're gonna extend this 4 units up. And mark it please. 1, 2, 3, 4 is about here. Alright, I can't make it bigger, but let's just take this longer. Here's 4. And this point was pi over 2 and 1. It's gonna be still pi over 2, but now it's gonna be 4 times 1, 4. So we are going to move it this high. Okay. Yeah, sorry for my poor skills, but got the idea. That part went up 4 units. Stretched actually, technically. And this part is going to go down 4 units. -4, let's say here. So we're gonna go sink to this level. Red dots still over there, they don't move. Do you see? Okay, we are gonna re-mention this, but this maximum it makes from the ground level, this stretch, it used to be tiny, now it's 4 times. There is a special name for this. Do you know what its name? What is it called? Anyone heard of it? It's called amplitude. This is called amplitude. So standard amplitude of sine is 1. This is 1. But when I have a number in front, new amplitude is 4 times 1, which is 4. So the numbers in front changes amplitude. And it's true for this side again. It goes 4 times down. Alright, I think you got the idea. Right? Make sense? Let's try this. Alright, in these questions you may think, oh, this homework is easy because only you need to pick the right option. That's not a healthy way of doing it. Don't peek at the solution options. Don't look at these. First, as I did on paper, finish the question yourself, then go pick the right option most similar to your answer. Don't go with the options here, okay? Then you won't learn. You will just test that, oh yeah, this looks like the best. No. Alright, which one is mine? First off, this is a cosine function. It's not right. This is cosine, no. And this is cosine as well. It went down. We need to start at 0. My picture should be starting at 0. This makes sense. D makes sense. Not C, not B. A makes sense, it starts, well, we should be going up, so it's D, right? Our picture is going up, so this is option D. Because in later questions you don't have these options, you need to make more work and decide other things. So always go with paperwork, then choose the right option. Alright, the second question is pretty similar. This time you have a number in front, but what is the difference? What do you see the difference? It's no longer a big number bigger than 1. It's a small number. 1 over 4 is less than 1. So it's going to shrink the picture. This is shrink. How much? You just multiply the amplitude. And by the way, this is for cosine. The graph changed as well, so you need to start with a period of cosine. This is one period of cosine. And shrink it 4 times. Get this original amplitude. Original is 1, size 1. We'll change to 1 over 4. Again, the points on the x-axis are frozen, nailed. These will not move. Only maximum and minimum values will move. What is the maximum originally? Here is one maximum, so you will only move these 3 points, that's it, and connect everything else. Move these maximums and minimums. This will drop to where? Here. 1 will drop to, just multiply 1 times 1 over 4. It will drop to 2.25. It's not here. You need to go further below. This is only half size. You need to go a quarter. So I will mark it here. Again, this thing is dropping to there. This thing will drop to 0.25 again. This 1/4, right? Again, this is 0.25. I know that from this computation. And this will again drop to here. Now connect these blue dots because green ones didn't move. You created the blue dots. Just connect them. Okay. Alright, it looks like part A is the right answer already. Is that so? Shrinked. No, this is a graph of sine. Upside down sine. It shouldn't be starting at 0. Look, it starts at 0.25. Where is 0.25 then? Is this the one? Nope. This looks like so. This is at 0, so it's C. Starts 0.25, 1/4 of the size. Seems correct to me. Alright, it's getting more challenging. This time you not only have a number in front, this is already what we built. You have now a number inside, in front of x only, not in front of the entire function. What does that number b does? This is new. It explains how b changes the graph on these pictures. Look, regular sine x is dashed 1. It has a period of 2 pi. It makes one mountain, one hill, one valley, one bump, one cavity, right? In 2 pi period. But when I put 2 in front of x, do you see this extra addition 2? It's not sine x anymore, sine 2x. The period drops to half from 2 pi to 2, like somebody divided this by 2, divided by this number, and it drops to pi now. That means it's going to make that one bump and one cavity only half the distance. From 0 to pi you're gonna make it. Instead of 0 to 2 pi you were making one bump, one cavity. Now you're gonna make that bump and cavity from 0 to pi, half the distance. And how do I know it's 0 to pi? This is the math you must be doing. Again, you start with this, it's 2 pi, 2x. You copy what you have here, 2x, into here. The regular period starts at 0 and ends here. I'm leaving 2x alone by dividing both sides by 2. Guess what happens? 0/2 is still 0, but 2/2 is just pi. So I know I must be doing one bump and one cavity from 0 to pi. 0 to pi, start your regular move, complete that period from 0 to pi. So I know I need to make a compressed picture. Look, this is compressed, like a spring, a wave. You push from this side and you compress it. Okay, let's talk about this side next. What's going on? They put a number in front of x, but that's not a big number, it's a small number, 1/2. Instead of 2, it's 1/2. I wonder what kind of change it's gonna make. Look, the original periods are from 0 to 2 pi, right? Correct? Now, what do we have inside sine? It's 1/2 2x. I need to leave x alone, so I'm multiplying both sides, all three sides, by 2. And we get 0 cancelled, x 4 pi. That means this is start, this is end. I will make one bump and one bump and one bump cavity within this period only. So it's a lot later now, relaxed, a lot relaxed, right? You used to do it quickly from 0 to 2 pi, one up, one down. Now you're gonna do it over an extended time, 0 to 4 pi. So I'm expecting a relaxation, not compressing. Look, it really relaxed. 0 to pi used to be the one bump. Now it's from 0 to 2 pi the bump. It's extended. Alright? And again, it used to be one cavity from pi to 2 pi. It's now 2 pi to 4 pi. So you put start and end here. Start, end, and pick the midway. This is the midway. Make one bump, one cavity. That's it. Okay? Alright? Okay, let's do this question then. Well, I'm giving you first ahead of time, couple minutes. Try to finish this on your own. What are the numbers? So do this later. This is later. First figure this out. Figure the green part out, then it's easy to make it 6 times later. Okay, ready? Alright, again, I'm ignoring 6. I will first do the transformation what 3 does, okay? So, I have no clue if this is going to be compressed or relaxed. I'm acting like I have no clue. I will just straightforward figure out the new start and end values. It used to be 0 to 2 pi, right? 0 to 2 pi. Put this 3x in. And let's figure out the new start and end. Divide both sides by 3. All 3 sides by 3. What do we have now? This is start. Here is end. So mark those values, please. Start is still this one. So this end does not change. Where is the end? I need to find it out. Where is it? 2 pi over 3. Oh, is it here? It's more than 2 pi. So I'm gonna relax it. Is it there? Where? Where's 2 pi over 3? If you're confused with the radian, this means 90. This means, no, that's not 9, of course. This is 180. This is 90. This is 270. This is 360, of course. What is 2 pi over 3 in degrees? Come on. 60? No, it's pi over 3 is 60. This is double. 120. Again, 180 over 3 is 60, but when you double it, it's 120. So where is 120? So you need to look at this really well, okay? It's crucial. 120 is a little bit past 90 here, isn't it? Correct? So right in the middle is 135. So it's somewhere here. 30 more actually. 120 is 90 plus 30. So you go 30 more. This is 90. So you go 1/3 of this distance. 1/3 of this distance. The first notch is good place. So this is where 2 pi over 3 is. Now please erase those 90s and 180s, I don't want to see them because they don't make sense. Alright, we now know where 2 pi over 3 is. What's gonna happen? This thing, this end value, it used to be right here. This end is gonna be pulled all the way here. Means it's going to make one dive, one climb. Okay, one dive, you dive, one long dive, one long climb between these two guys. Okay, so where does the dive ends here? Dive always ends in half distance. In the past, the dive ends right in the middle. So I need to figure out where this dive ends. So start, end. I need to finish it off. Start diving right here, correct? Right in the middle. So I will start right here. This is start again. It didn't change. Oh, am I doing it right? No. The dive must end here. I didn't finish it yet. So I need to go a lot earlier then. And how low? Up to -1, you need to dive. Dive, dive, dive. There's a slight turn here. Do you see? It's not straight. It looks like straight, but yeah, I'm gonna do it. Back here. It's such a big compression. Alright, much better. Alright, the dive end here, and then I start climbing. The right in the middle, the dive stops, and then I start climbing, and I'm gonna climb up here. So make the final picture. This is how high I'm gonna climb from here to there. So I will go and do this. Alright, I put this in dashed line because this is not the final answer. Why? We only did here the green part. What do we have here? We are going to make this 6 times deeper and higher. We're gonna stretch it 6 times, and I'm not sure I can do it on this picture. So you need to do, just imagine this is 6, okay? This blue point and that blue point is gonna climb up here to 6, and this -1 is gonna go up to -6 down here, right here. Alright, so this is a tough one. I'm gonna go zoom out. That's too much. Let me finish this off here first. Yeah, this is a really skinny one. Do you get it? Okay. I don't even make the entire 6. 6 becomes really up high, but you got it, right? Okay. Don't worry, in the Connect Math they already give you options, so you don't have to make it there. But you need to answer a few questions before. What is the new amplitude? Amplitude is the scale. You go from bottom, ground level to the maximum. What is that new? It's 6. It used to be 1, but we multiply it by 6. It's 6. What is the new period? Oh, I didn't tell you what's the new period. Look, it completed a dive and climb from what start to end value. What is this distance? New distance. This is called the period, new period. It used to be 0 to 2 pi, and it's now what? 2 pi over 3. Where do we find it directly? It's this one. This number, it used to be period. Now this is the new period, 2 pi over 3. You always divide 2 pi by b. It's actually 2 pi versus b. b is here 3. Alright, so this is 2 pi over 3. Now we get to pick the right answer. It needs to make 0 to 2 pi move. So make sure all 0 to 2 pi over 3. They are all 0 to 2 pi over 3. 0 to 2 pi over 3. Everybody is the same. So I need to go with another criteria. It starts at 6. Which one is starting at 6? Not A, not B, not C. We already have a winner here. It's D. We didn't mark it, but the midpoint is pi over 3. This mid value is pi over 3. It's actually half of this end value always. 2 pi over 3 becomes pi over 3. It's more visible here. And the key points, they're asking for key points. I don't mention this, but they are asking for these key points. Here. Maximum and minimums. Okay, these maximum and minimums are asked 1, 2, 3, 4. 1, 2, 3, 4. They're asking for this. So for cosine, it's the first time it meets x-axis and then makes minimum, and then meets next time x-axis and makes maximum. So what is the first time? You can just read it off from the screen. Wait a minute, this has 5 though. I'm not 100% sure which 5 they're asking. 1, 2, 3, 4, 5. Probably initial value, first x-intercept, minimum, second x-intercept, and maximum value. So let's go with them. They want this 0, 6. This is 0, 6. This is pi over 6, 0. So we may need to cheat and see what kind of answer they want from checking it. The second one is this one. It's pi over 3 and negative 6. This minimum value. And the last one is 2 pi over 3 and 6. Did I type them right? No, I missed one. I missed pi over 2. Anyhow, let's check. It's gonna say incorrect. Let's see what kind of answer they want. After a while, they need to say the right answer so we can know. They insist. Alright, I'm going to pick it pi over 2, and this is
You have to solve it, but yes, I do.
Yeah, let's do that. Let's cheat. I don't want to waste time on it. Yeah, they want, as I said, they want this initial first intercept, minimum, second intercept, and last point in parentheses point notation. I was doing it right, but I don't have the patience. Okay. Alright, so this is it. We'll continue this tomorrow. There's still more left. We're gonna do phase shifts and also do horizontal and shifts as well.